This is part 15 of square roots and radicals, and we're going to begin with how to divide with square roots. So the quotient rule for square roots simply says the square root of a quotient, the square root of a over b, is equal to the square root of a over the square root of b. Now, we've done some of these problems in previous videos. So for instance, if you had the square root of 16/9, you could say, well, what number times itself equals 16/9? And some people realize it's 4/3 because 4/3 times 4/3 equals 16/9. So that's the principal square root, right? But another way of doing this is to split the numerator and denominator up. So you have the square root of 16 over the square root of 9, and we get 4/3. And that's a little easier for most people to just simply think of the square root of 16 and the square root of 9. So here's another problem. The square root of 18/25. Well, we could write that as the square root of 18 over the square root of 25. Now, in the denominator, square root of 25 is the integer 5, but square root of 18 does not come out perfectly. So you could figure this out on the side somewhere in your scratch paper. So let's do that. Square root of 18 is the square root of 9 times 2, and you could take a 3 out. So therefore, the square root of 18 would be 3 square roots of 2. Now you could do that all up here in the same spot. I just thought it might be kind of messy looking. So this would be the answer, 3 square roots of 2 over 5. Now some people think of that as 3/5 times the square root of 2. That's all right too. I think it's easier to leave it as a fraction. All right, here's a different problem. Simplify the square root of 12x cubed y to the 5th over the square root of 3xy. In this case, it's easier to go backwards and write this as one big square root to see if anything cancels. So I have 12x cubed y to the 5th over 3xy, all under one radical sign. And now we can simplify that fraction. 12 over 3 is going to be the 4. And I have x cubed over x. That'll be x squared. Remember your laws of exponents where you can subtract the exponents, 3 minus 1. And y to the 5th over y, same reasoning, we'll get y to the 4th. And now actually everything under here happens to be a perfect square, right? 4 is a perfect square, x squared and y to the 4th are all perfect squares. So what would pop out then is the 2xy squared if you wanted to write it, or you could just write that at the next step. So that's how that simplifies. So you could use the quotient rule either way. All right, let's look at this problem. Simplify the square root of 1/2. Well, this would be the square root of 1 in the numerator over the square root of 2 in the denominator. And the square root of 1 is 1, and I get 1 over square root of 2. Now, there's something we do in math. We don't leave answers with square roots in the denominator. And the reason for it, I think, comes from doing arithmetic computations before there were calculators. So, for instance, if you right now knew the approximation for square root of 2 was 1.414. Now, actually, that's an approximation. It goes on forever and ever. Square root of 2 is an irrational number. But let's say that you know that square root of 2 was 1.414, not because you had a calculator, but because you were given that. And somebody says, well, I want to approximate what 1 over square root of 2 is. Well, that means that I could take and compute 1 over 1.414 and get sort of a rough idea what that is. And again, if I'm not using a calculator, think about this. This kind of becomes a long division problem, right? I don't know how many places I'm going to have to go. You got to move the decimal here 3 to the right, correct? Then I have to think, okay, how many times does 1,414 go into 10,000? And it goes in 7 times. And then I have to multiply 7 times 1414, and that's actually going to be 9898. And then I have to subtract, and that's 102. And then what do? You bring down the next 0, and that does not go into that, so then you have to add a 0 here and bring down the next 0. And let's see, so the first time I had to put a 0 here, the placeholder, because it didn't go into 1020. Then I bring the next 0 down, goes into 7 again. Then I've got to subtract 98, 98, and that's 302. And, then I'd have to bring down another 0. You can see, this is not really fun to do. Most people don't like doing long division as it is, especially having to divide by a 4-digit number. So that's just sort of the motivation for you to think this is what you would have to do. First of all, you'd need to get some sort of approximation. And of course, imagine if you went out 10 digits, this would even be a longer long division problem. So let's look at this 1 over square root of 2 again. So I've got 1 over the square root of 2. All right, now remember we had this property, square root of x times square root of x always equals x. So if you have a square root of something, if you multiplied by the same exact square root, you wouldn't have a square root anymore. So in other words, square root of 2 times square root of 2 is just 2. Square root of 3 times square root of 3 is just 3. Square root of 5 times square root of 5 is equal to 5, and so on. So there's a little trick here. This is a fraction, and we're going to make an equivalent fraction. Remember, you could take any fraction and multiply the numerator and denominator by the same thing. If I multiplied the denominator by square root of 2, what would happen is I'd have a 2 in the denominator because I'd have square root of 2 times square root of 2 because of this property. But you can't just multiply the denominator by that. You have to multiply the numerator as well. So 1 over square root of 2 is equivalent to square root of 2 over 2. And notice I don't have a square root in the denominator now. This is called rationalizing the denominator. So remember, a rational number does not have any square roots. It's a whole number, 5, it could be written as a fraction, etc. So 2 is a rational number. The idea is you're making a rational number in the denominator. Now, why is square root of 2 over 2 easier to compute? Because if I know again that 1.414 is an approximation for square root of 2, look at how much easier the division is. If I just do 2 into 1.414, look at how simple this is going to be. I'm going to get 7, 0, bring down the 4, 7, and I'm done. Look at how quickly I got 0.707. All right, just to remember what it looked like before, I got 0.707 doing it this way, but a lot more arithmetic along the way. So I think that was the motivation originally for rationalizing the denominator. But the point is we do not leave square roots in the denominator, and we're going to use this trick. So let's do it on another problem, and then in the next video we'll do a lot more problems and we'll figure out how to do other kinds of rationalizing the denominator when it's just not a simple square root. So let's say you wanted to simplify 3 over the square root of 5. Okay. I have a square root in the denominator, so I'm going to use that trick of multiplying the numerator and denominator by square root of 5. And now I've got 3 square roots of 5 over 5, and that's my answer. I have now rationalized the denominator. So if it says simplify, that means do not leave a square root in the denominator. Let's look at another problem. How about 12 over the square root of 6? Okay, so again, I've got a square root in the denominator, so I need to multiply the numerator and denominator by square root of 6. So I have 12 square roots of 6. Now, square root of 6 times square root of 6 is just 6. Now, on the outside of the square root, I've got a 12 in the numerator and a 6. These can be canceled, so that my final answer is 2 square roots of 6. So this is just a little introduction to dividing with square roots so far and rationalizing the denominator, and we'll do a lot more examples on the next video.